Hi there, how's it going? This video, I'm going to be talking a little bit about just good old regular Newtonian gravity. Um, if any of you know a little bit about me or know me, um, you probably know that I have this strange obsession with a hypothesis of gravitational absorption, um, which finds its roots. Well, hell, I don't know how far back, but there's definitely some history in the early 20th century, which is pretty interesting. You can find in the history of astronomy that there were lunar fluctuations, secular accelerations perhaps they may have been called, in the late 1700s and in the 1800s. Newton said the moon was the only problem that ever made his head ache, and it's just interesting that his theory of gravity would work so well, but the celestial body which was closest to us was the one that was the hardest one to, and the one that we could see the best was the one that was most difficult in explaining with the theory. And basically 100 years after the Principia was published, the mathematicians of the time, Simon Pierre de Laplace, particularly, had thought they had finally figured out, and understood the last of the problems with the moon gravitationally, but most people agree, even at that time, and still today, there are still problems with the moon which technically don't have a true gravitational explanation. And as late as the 1910s and 1920s, certain scientists or theoretical scientists were talking about what it would mean if perhaps there was a slight gravitational absorption during a lunar eclipse. So, like, the sun exerts its gravity on both the sun and the moon. And they said, what would happen if, when the Earth was between the sun and the moon, the sun's gravity upon the moon was slightly weakened or slightly absorbed by the Earth? And so they tried to figure out what the moon's orbit would have to look like if that happened. And it actually was a striking connection, that the correlation. They saw that for a couple of years, or maybe a few years, some physicists or theoretical scientists actually thought that had to be happening. They thought there was a slight gravitational absorption because it matched up with the observations, the real orbit of the moon. But the match was not perfect, and eventually the idea kind of fell by the wayside. But it definitely should not be forgotten. I think it still might be useful to us today. But in any case, I just think it's interesting to go back and maybe practice a little bit with just the traditional Newtonian stuff, kind of with with those curiosities in mind. And one of the first questions I asked myself was, well, how strong is the sun's gravity upon the moon as compared to the Earth's gravity upon the moon? And if I remember correctly, the ratio that I came up with when I first tried to do a very basic calculation was about 7-4. The sun's gravity on the moon, and by that I mean the strength with which the sun pulls upon the moon is stronger than the strength with which the Earth pulls upon the moon, by a ratio of about 7-4. Now, I don't know what kind of numbers I've plugged in there, but I think if the book from Isaac Asimov, which I have, if he was more accurate than I was at that time, and since I've repeated the calculations with so the numbers that I got from Wikipedia more recently, it seems like he was closer. Although he still seems to have been higher than what I can get using the numbers on Wikipedia. But he said the ratio was, oh, I'm sorry, the ratio was not higher, but it was close. If you turn the ratio around, it would have, Asimov's would have been higher. If you say what fraction of the sun's gravitation the Earth's gravitation reproduces, his number was 0.46. So measured against the sun's gravitation on the moon, you say, what's the Earth's gravitation on the moon? And he says, well, it's 0.46 of that. And apparently I seem to be getting 0.42 or something pretty close. But it's just an interesting exercise, and I might make a few more videos here to show some of the calculations which I've made. Okay, I'm back. Let me just say that the value that I got for the Earth's gravitation upon the moon compared to the sun's was closer to Asimov's than I said. Asimov's was 0.46, and this is in the book On Time and Space and Other Things, or whatever it's called. So his fraction was 0.46, but mine, I said it was 0.42, but I got 0.452, so pretty close to 0.46. And I'll just show some numbers that I used, which I just got from Wikipedia. Okay. Here is the Earth's mass, 5.97219 times 10 to the 24th kilograms. But actually I rounded that to rounded it to I don't know how you write a symbol for, if anything, I rounded it down, not up. What kind of symbol is that? I just rounded it to 5.97 times 10 to the 24th kilograms. And first I actually compared the strength of the sun's gravity upon a human body at the Earth's surface, and the Earth's gravity upon a human body. But maybe I'll come back to that later. Instead, let's look at the Earth and Sun upon the Moon, as I was speaking before. And so the distance, or I'm sorry, the mass, for the mass of the Moon, I was using 7.35 times 10 to the 22 kilograms. And like I said, I don't know, maybe Wikipedia gave a few more numbers after the decimal point. But anyway, that was the value that I was using. And the distance between these two, I don't know, average distance, or maybe it was the semi-major axis of the Moon's orbit, perhaps. But I used the value 3.844 times 10 to the 8th meters. Okay. And so the equation, which I wrote out, and because we're comparing two different gravitational equations, I just conveniently dropped out the gravitational constant in each equation. So all I had was m1 times m2 over the distance squared. So 5.97 times 10 to the 24th times 7.35 times 10 to the 22 over 3.844 times 10 to the 8th, and that whole thing squared. And so this is the gravitational force between the Earth and the Moon. And what I got was about roughly 2.97 times 10 to the 30th, and oh gosh, I don't know if that would be newtons, or I don't know if there's any units there, but all I'm doing is comparing that number to the number that I'm going to get for the gravitation between the Sun and the Moon, which, and for that I've used 2 times 10 to the 30th, which is the rough estimate for the mass of the Sun times the mass of the Moon, 7.35 again, times 10 to the 22. And the distance here is 1.496 roughly times 10 to the 11th meters. And you got to square that whole thing. And from that I got 6.57. Sorry, that's a roughly 6.57 times 10 to the 30th. So you see the 10 to the 30ths are the same, and so we just take the ratio of 2.97 to 6.57, and like I said, that was about 0.452. So very close to Asimov's 0.46. So very fascinating, that the sun's gravitation is very strong from very great distance. Yeah, I guess I'll take a break here. Maybe I'll come back and talk about that comparison between the sun and the earth upon an actual human body at the surface of the earth. And of course, the comparison's the same, whatever kind of body. You could be talking about an elephant or an ant. The ratio, the comparison will be the same as long as you're talking about the same spot in space. Alright, anyway, take a break. Hopefully I'll see you again. Alright, here we are again. Just a few comments I'd like to add to that previous video. As you saw when I said I rounded the value for the mass of the Earth, I rounded it down to 5.97 times 10 to the 24th kilograms. So that may have been the main reason, perhaps, why my value was a little bit lower than Mr. Asimov's. And what else would I... Oh yeah, now these numbers that I was comparing, 2.97 times 10 to the 30th to 6.57 times 10 to the 30th, those would have been, since I dropped the gravitational constant, those would have been in kilograms squared over meters squared. And maybe from that you can figure out what units must be in the gravitational constant, because using the gravitational constant you have to get newtons in the end. But yeah, I guess that's all I wanted to say about that last video. Now I'm going to be talking about comparing the sun's gravity and the Earth's gravity as it acts upon us upon the surface of the Earth. So the radius of the Earth roughly is about 6.371 times 10 to the 6th meters, and what else here? As I was saying before, the mass which I will plug in for an object at the surface of the Earth, I'm just going to plug in the number 1, because like I said, it doesn't really matter how much it weighs in the calculation that we're doing. And that will make our calculations a bit easier. So let me say G1 will be 5.97. Oops, sorry. 5.97 times 10 to the 24th. And like I said, I'm just going to multiply that by 1, so a little bit redundant, forgive me. And we'll put this distance, so G1 will be the effect of the Earth's gravity upon an object at the surface of the Earth. .371 times 10 to the 6th meters squared will get us roughly, what would that get us? 1.103 times 10 to the 13th. 10 to the 13th. Does that look right? What do you think? Alright, and then we're going to compare that to the sun's gravitation upon an object here at the surface of the Earth. So we'll plug in the sun's mass, 2 times 10 to the 30th times 1, and the distance, 1.496 times 10 to the 11th squared. Boop. And that will get us about 1.5 times 10 to the 10th. And so, from these numbers, let's see if you were paying attention. We said the sun is actually stronger in its effect upon the moon than the Earth is upon the moon. Now, what do you think it would be for an object here at the surface of the Earth? Is the Earth stronger or is the sun stronger? I already showed you. But anyway, here it is again. The Earth is stronger, significantly stronger. I'm sorry, I got this value wrong. This was 1.5 divided by 2.238. Forgive me, forgive me. I got this right. That comes out to be roughly 6.7 times 10 to the 9th. Okay, so the Earth still wins here. Basically, when you compare these, you see that the Earth's gravitation is about 1,600 times stronger. (1,646 times stronger than the sun's gravity here at the surface of the Earth. So it's a little bit different, quite a bit different from what we saw with the moon, and that's not too surprising. One interesting question we might ask is how much would those numbers have changed for the moon, the sun, and Earth compared in their actions upon the moon. If we had in turn made a comparison between conjunction and opposition, or when the moon is closer to the sun as opposed to when it is farther away from the sun. Now, it'd make a difference, but not a huge difference. Anyway, that's for another time, another video. But anyway, yeah. So you see, if say you have a large creature that weighs 1,646 pounds here on the surface of the Earth. Well, wherever the sun is, according to Newtonian theory, there is 1 pound of force for that object going toward the sun because of the sun's gravity. Alright, hope you enjoyed. Very exciting stuff. We'll see you. I just want to acknowledge that I made a pretty big mistake in that last video, the calculations I made. I said I was making everything simpler by making the mass of the body of the object at the surface of the Earth a value of 1 kilogram, and I just screwed everything up by doing that because I was copying the values which I had calculated the first time, and the first time I did the problem I used a value of 75 kilograms. So if you go back and you look at the numbers, if you plug in 75 instead of the 1, you'll see why I got the numbers I did. But the final comparison and the ratio of 1,646 to 1, that still holds. That's still a legitimate ratio. Sorry about that. Alright. Even the best of us make mistakes. Okay, thanks. Later.